This is the technical instructions for Hydrocyclone gas cleaner design in my Excel workbook. For this, there are 9 steps for using this Excel workbook to design a hydrocyclone. Step 1 is the instruction overview. This includes that these highlighted yellow cells are for user inputs, and the blue cells, highlighted blue cells, are for outputs that are calculated from the Excel workbook. The second step is to go ahead and select a system design for the cyclone geometry. This is where you can go to the drop down next to the system design, and there are 5 options here. With this little table here over to the side, you can see that which systems are for high throughputs and which ones are for high efficiencies. If a value is instead accidentally entered, an error will occur. By hitting cancel, you can go back to select a different system. Next, step 3 is to input the diameter of the value for the cyclone. Here we have 0.8 feet as an example. The user would input their own. Step 4 is to input the flow rate, the temperature, and the pressure, which are all the initial conditions for the inlet stream. It is important to note that none of these values can be a negative number, or the flow rate and pressure cannot be a negative number. The temperature cannot be below absolute 0. For example, if we were to put negative 50, we can see that the flow rate must be greater than 0. If you retry, we can put in a different value, or by hitting cancel, we reset to the old value. Step 5, is to set the inlet composition of the flue gas stream. Here, the values need to be between 0 and 1, and you need to, or else an error will occur. Again, hit retry to do a different value, or cancel to restore the original value. If the sum of all of the four for carbon dioxide, oxygen, nitrogen, and water vapor mole fractions is greater than 1, a warning will appear saying, warning, invalid system composition. Be sure to double check your values and possibly maybe round a little bit different. For example, rounding 0.666 to 6.67 to get this to equal to 1. Step 6 is then to input the particle weight distribution of the dry ash. Similar here, we have the different ranges for the particle diameter in micrometers, and we will input the different weights here. These need to be values from 0 to 100. So you see here again, retry to put in a different value, cancel to restore the original. And if this value is over 102 for the sum of all the different weight percents, it will say invalid system weight distribution. Again, double check all of your values and possibly round a little bit different. The 7th step is to analyze, or is to use the particle diameter efficiency calculator. That is this right here. Again, yellow highlighted is for input, blue is for calculated output. Go ahead and put in a particle diameter such as 10. A good rule of thumb is to have 10 at least 95 or higher and 5 at least 90 or higher. This is the efficiency at which the cyclone will remove this particle size. The 8th step is to, and for this 7th step here as well, if you are meeting your requirements such as that 90-95, you can also go ahead to the system design and possibly look at maybe some high throughputs here to make sure you're using one of those for the highest throughput with still meeting the required efficiencies. Step 8 then is reading and interpreting the variable output values. That is this section here. We have 5 different things that are calculated that are overall efficiency, particle cutoff diameter, pressure drop, inlet velocity, exit velocity. The overall efficiency is the efficiency of the overall hydrocyclone system. If this value is greater than 100, for example, you will see a warning here where this efficiency is not possible because you cannot have over 100. Again, just for your entire, all your inputs, make sure that the values are correct. And there aren't any already existing warnings or errors that are present. The particle cutoff diameter is the diameter of particles that are at 50% efficiency for the machine. The pressure drop is the difference between the feed and the overflow pressures. It is important that this value is not too high and usually lower than around 5, or else some particles could be pulled into the overflow that should be going to the underflow, and this could dramatically reduce efficiency. And the final step is reading the dimensions here, which is in this little table. There is a name for each of them, the corresponding letter, and then out on in the model here, we can see that you can find the different letters that correspond to their names and their dimensions that with arrows pointing to them as well.